All right, so we got this question from a student. What are inverse matrices? How do they contribute to representation of linear systems? And how does one solve for them? Now, at this point in the semester, inverse matrices may have been mentioned in the class, but it's going to be, if I had to guess, about 3 or so weeks until you guys actually cover the topic. So in this video, I tried my best to balance the need to go over material that hasn't been covered yet while still keeping the video brief. It's possible that you won't fully understand everything in this video though at this time because I touch on topics that haven't been covered yet in the class. First, I want to make sure everyone knows what a linear system of equations is. So here I've written down an example of a linear system of equations. So this particular example has 3 equations and 3 variables to solve for, x, y, and z. In general, a linear system of equations could have any number of equations and any number of variables. Okay. What makes this a linear system of equations? So first, none of the variables are being raised to any powers aside from a power of 1, because x is already x to the 1. But you don't see anything like x squared, for instance. So there's that. Also, none of the variables are multiplying each other. So you don't see any terms like x times y in any of the equations. None of the variables are dividing each other either. So all we have is our variables are being multiplied by numbers, and then they're being added or subtracted after that. So that's what makes it linear. Now, the simplest case would be when you have one equation and one variable to solve for. Okay. So a linear equation with just one variable in it would look something like this. We'd have a variable x, and because it's linear, it's not being raised to any power. It's just x. It'll possibly be multiplied by some number, and then it'll be set equal to another number. And in this simplest case, we know how to solve for x already. So if we wanted to solve for x, what would we do? We would divide both sides of this equation by a. And dividing by a is the same as multiplying by a to the negative 1. So I'm going to write it like that. A to the negative 1 times a is equal to 1. So on the left, we end up with 1 times x. And then 1 times x is just x. So in the end, we find the solution x must be a inverse times b, which is the same as b over a, of course. All right, so that was so easy to solve for x. What we would like to do is to be able to generalize this to a larger linear system of equations. And that's where we'll need the notion of a matrix inverse. So in order to get to that, first I want to talk about representing a linear system of equations using matrices. So let's take the example that I have up here. And I'm just going to rewrite my linear system of equations. So I'm going to take the coefficients of x, which were 1, 2, and 0. I'm going to take the coefficients of y, which are negative 1, 1, 2. And then the coefficients of z, which are 2, negative 3, and 1. So we can put those into a matrix. And if we multiply that matrix with the vector x, y, z, so the vector of unknowns, then that would be set equal to the right-hand side of our linear system of equations, 6, 1, 4. Okay, so the matrix of coefficients here, we'll call that A. The vector of unknowns, we'll call that a vector x. And then the right-hand side, we'll call that a vector b. Okay. So you can do this with any linear system of equations. And we do that partly so that we can relate it more easily to the situation that we had over here. Okay, so you see how these equations, they look very similar to each other. Ax equals b. So let's see. Let me write down the general matrix equation Ax equals b here. So if we wanted to generalize this, so we would need some notion of an inverse of a matrix A. And if we had such an inverse, we could multiply both sides by A inverse. Okay. Now, what happened here was A times A inverse gave us the number 1. So we'll need some kind of generalization of the number 1. So I'll put the number 1 here, but I'll maybe put a question mark as well. So we'll get to that. Okay, but something like that would happen, and then 1 or whatever that is going to be times x. We'd want that to just be equal to x, so that in the end, we could say that the solution to our equation is given by A inverse times the vector b. All right, so let's talk about this this sort of mystery number 1 that we have here. So instead of having the number 1 here, instead we're going to have identity matrices play the role of the number 1 in general. So let's quickly talk about identity matrices. So an identity matrix, it's a matrix that has 1s along the diagonal and then 0s everywhere else. So here I have a 2 by 2, and then this is a 3 by 3 example of an identity matrix. Okay, so we usually use the letter I to denote an identity matrix. And sometimes we'll put a subscript to indicate what the size of the identity matrix was. So I2 is the 2 by 2 identity matrix. I3 is the 3 by 3 identity matrix. And if we don't care so much about emphasizing the size, then we'll just use I for an identity matrix. All right, so what's special about identity matrices? If you take an identity matrix and you multiply it with a matrix A, basically nothing will happen and you'll just get the matrix A again. Likewise, if you multiply a matrix on the right by an identity, again, you're just going to get the original matrix. So this is a property that identity matrices satisfy. You can verify that yourself. So for instance, let me take the 2 by 2 identity matrix. Let's say we were to multiply it with a 2 by 2 matrix. So you should check to actually carry out the multiplication. And you'll find that indeed you just get A, B, C, D when all is said and done. All right, so this property of identity matrices Notice how similar that is to the number 1. So it's similar to how 1 times any number will just give you that number. So in other words, basically, identity matrices are the matrix version of the number 1. Okay, so that's kind of the main takeaway that you can take from this. Okay. So then the idea is over here, instead of having A inverse times A being equal to 1, it seems more appropriate that we'd have A inverse times A giving us an identity matrix. Since A itself is a matrix. And identity times anything will just give you that thing. So everything here will still work out. Identity times x will still be equal to x. So you'll still end up with x equals A inverse B. So with that, we can now define what the inverse of a matrix is. I'll do that at the bottom. Okay. So we say that a matrix A is invertible if there exists a matrix B such that B times A equals an identity matrix. Now, if A is invertible, so if there is such a matrix B, for which B times A is equal to I, it can be shown that the matrix B is unique. We denote the matrix B as A to a power of -1, and we call it the inverse of A. Okay, so note that not every matrix is invertible, so some matrices do not have inverses. Another fact which I'm just going to mention real quick is that for a matrix to be invertible, it has to be a square matrix, meaning its size should be n by n for some number n. Okay. Now let's talk about how to find the inverse of a matrix. So once we are able to find the inverse of a matrix, we would at least be able to solve a linear system of equations like this if the matrix A was invertible. So let's talk about how to find the inverse. And I'm just going to give so there's a couple ways of finding the inverse of a matrix. I'm just going to describe one method of doing so. And I'm not going to explain how this works. If you want to understand how it works, though, you can read about it in the book that I wrote for this class. But I think it takes a while, and I don't want this video to be too long. So the way it works is you take the matrix A, and you will augment it with an identity matrix on the right. You're going to perform row operations until you've reduced A to an identity matrix on the left. Then whatever you end up with on the right will actually turn out to be the inverse of A. So I'm going to illustrate that using the example that I started with. So let me take this matrix up here. And let's try to find the inverse of this guy. Okay. So according to this algorithm up here, I'm going to take the matrix that we have, I'm going to augment it with an identity. Now what I need to do is I need to perform row operations until I get an identity matrix on the left. Okay, so first let's do row 2 minus 2 row 1 to eliminate this 2. So row 1 will be unchanged. Row 3 will be unchanged. But we are subtracting 2 of row 1 from row 2. So we'll get a 0 here. Row 2 minus 2 of row 1, that's going to be 1 plus 2 will give us a 3. Negative 3 minus 4 will be negative 7. Over here, 0 minus 2 will be negative 2. 1 minus 0 is 1. And 0 minus 0 will be 0. Okay. All right, let's see here. Since I want to get an identity matrix on the left, so I want to turn this 3 into a 1. Maybe what I'll do for that is I'll continue over here. No, whoops. Okay. So what I want to do is, I think I'm going to do row 2 minus row 3 real quick. Because that's going to give me a 3 minus a 2, so it'll give me a 1 in this position. And if I do row 2 minus row 3, minus 7 minus 1 is minus 8. Minus 2 minus 0. 1 minus 0. And 0 minus 1. Okay. All right. And now let's see here. So I need to make these two numbers zeros. So let's do row 1 plus row 2 to get rid of this negative 1. And we'll do row 3 minus 2 of row 2. And that will eliminate this 2. Okay. So I'll copy down row 2 first. All right, so let's see. If we do row 1 plus row 2, we should get negative 6. Negative 1, 1, negative 1. Row 3 minus 2 of row 2. That's going to be 1 plus 16, so 17. 0 plus 4. 0 minus 2, and 1 plus 2. Okay, and hopefully I haven't made any mistakes. All right. So now, let's see here. I'll go ahead and make this 17 a 1. So I'm going to just multiply row 3 by 1 over 17. And finally, we'll do row 1 plus 6 of row 3 and row 2 plus 8 of row 3. And that will give us an identity matrix on the left. So whatever we end up with on the right should be the inverse of A. Okay. Now let's see here. I'll copy down row 3. And let's see here. I'll do row 1 first. So we're adding 6 of row 3. That's 24 over 17. So I think we'll get 7 over 17. So what is this going to be? So it'll be minus 12. So I think that'll be 5 over 17. It'll be plus 18. So I think 1 over 17. And then row 2 plus 8 of row 3. Let me see, so that's 32 minus 34. So negative 2 over 17. So it'll be minus 16. So it'll be 1 over 17. And then it's 24. So 7 over 17. All right, so assuming I made no mistakes, then that would be the inverse of A. All right. Okay, so for this matrix A up here, we have its inverse down here at the bottom. So now let's use this and let's try to solve that system of equations that I started this video with. So this was the original example that I started with. Here we have it written as a matrix equation. And we just found the inverse of A. So we have that result. Now remember, if we have the equation AX equals B, we can multiply both sides by A inverse. And that will leave us with the solution X being equal to A inverse times B. Okay. So let's use the inverse that we just found, and let's try to get the solution to this linear system of equations. So vector X was the vector X, Y, Z. So we're saying it should be equal to A inverse. And let's see here. Let me pull out the 1 over 17. I'll pull it out from the A inverse matrix. Okay, so that's A inverse. And then multiplying with the vector B, which is 6, 1, and 4. Let's multiply this out, and let's see what the solution should be. So I'll keep the 1 over 17 in front for now. So we're going to get, let's see here, 42 plus 5 is 47, plus 4 is 51. We're going to get negative 12, plus 1 is negative 11, plus 28. So negative 11 plus 28 should be 17. And then here we get 24 minus 2 is 22, plus 12 is 34. And all of these numbers are actually divisible by 17. So 51 over 17 is 3, 17 over 17 is 1, and 34 over 17 is 2. So with that, we get the solution X should be equal to 3. Y should be equal to 1, and Z should be equal to 2. Now, you can actually check by plugging these numbers in to the original linear system of equations. Okay, so if we did in the first equation 3 minus 1 plus 2 times 2, plugging in 2 for Z, that does indeed give us 6, so that checks out. And you can check the other ones and everything works, okay? All right, so that was just a very quick run through on matrix inverses, what they are, how to compute the inverse of a matrix, and how I can use it to solve a linear system of equations.